For problem 1 in chapter 25, we're given a gauge wire made of copper, and we're asked to find some of its properties. The current density, which we denote by J, is the current over the area, and the area, since we have a wire which has a diameter, we can write as pi d squared, where d is the diameter, over 4. And plugging these numbers in, we have pi times 1.02 times 10 to the minus third meters quantity squared, all over 4. And that gives us a value of 8.17 times 10 to the negative 7th meters squared. So now we can say that J, the current density, is 1.67 amps, which is the current that the wire carries, over this 8.17 times 10 to the minus 7th meters squared, or 2.04 times 10 to the 6th amp per meter squared. For part B, we're asked to find what is known as a drift speed, and that's the speed that the electrons would have in order to generate the current. The drift speed is given by the current density over the number of electrons density times the absolute value of each one of those charges. And we just found what the current density is, 2.04 times 10 to the 6th amp per meter squared. We're told what the density is. The free electron density is given as 8.5 times 10 to the 28th electron per meters cubed, times the charge, which is 1.6 times 10 to the negative 19th coulomb per electron. And if we do this, we get about 1.5 times 10 to the negative 4 meters per second, which is about 0.15 millimeters per second, if you want to think of it that way. The next part is asking for the magnitude of the electric field, and the magnitude or the electric field is given by the electric field E can be given by the density times the current density, the resistivity, I should say, times the current density, and this is rho I over A, again because J is I over A, and we're told that the resistivity for this wire is 1.72 times 10 to the negative 8 omega meter. The current we know is 1.67 amps, and the area we found earlier to be 8.17 times 10 to the negative 7 meters squared. Putting all of these numbers together, we get about 0.0350 volts per meter, which is what the electric field is. Part D, It says find the potential difference. The potential difference is the electric field times the length. We've seen this in the earlier chapters. So this is going to be 0.0350 volts per meter times the length of the wire segment, which is 50 meters, or 1.75 volts. And lastly, we're asked to find the resistivity and the resistance, and we know that the resistance is the resistivity times the length over the area, which we can find as 1.72 10 to the minus 8 ohm meter times 50 meters all over the area, which is 8.17 times 10 to the minus 7th meter squared. This gives us a resistance of 1.05 ohms, or if we remember what Ohm's law says, we know that R equals V over I from Ohm's law. So we can say that R equals the voltage, which is 1.75 volts, divided by the current, which is 1.67 amps, which also gives us 1.05 ohms. So either way, we get the same answer.